Okay, I'm going to give a quick introduction while we're starting this out, but sorry for the slightly late start. Thank you so much to everybody for coming. This is our final professor lecture of the semester. So I am very happy to welcome Professor Gordon Stacey. He is a professor with the Astronomy Department and also the project director for CCAT. And as soon as we get the screen sorted out, we will begin. Very sorry for technical difficulties. Yes. He was also apparently our advisor for 2 non-consecutive years.
Screen sharing is stopped because the external, I reconnected it.
Oh, we got it back. We got it back. Well,
got
screen sharing is not back, but connection is back. Okay.
So I wonder
Okay.
if this will work then, if I can do it this way. Now, where's my mouse? Yeah, I think over there.
And just make sure.
Did I push OK? No,
Oh, is your screen touchscreen?
Yeah.
Oh, sweet. Okay.
Yeah, the touchscreens are nice.
I know. That should be good. And you are good to go.
Hi. Thank you, Jillian, for inviting me to come and give this lecture. I'm happy to be here. Happy to learn what the inside of these great buildings look like and wish that our space sciences building looks similar. But so I'm here to talk about the CCAT project, and it's an international project led by Cornell. I guess it's been going on in some way or another for 25 years. Became the current version about 10 years ago or so. And the current version involves this modest aperture telescope on a peak in Chile. I'll tell you more about it, called Chattanooga. And it's a 6-meter diameter telescope, which doesn't sound enormously large, but what is great about it is that it has an enormously large field of view. So for that sort of science, it's excellent. It's there now, so it should work. So the telescope is called the Fred Young Submillimeter Telescope after our donor, Fred Young. And it's pronounced feast, and so he is truly the founder of the feast indeed. And no references to movies, okay. It's a 6-meter dish. It's very high precision for submillimeter telescope. We're working in submillimeter bands. It's located at 5,600 meters elevation, which is 18,000 feet on this mountain called Cerro Chattanooga in the Atacama Desert in northern Chile. So it's a novel design. I'll give you some insight to it in a couple slides. And it has, it's at its exceptional site. It's the highest site to which one can drive a truck with an asterisk because there's actually a telescope called Tau about 60 meters higher than us, but they help us pay for the road. And it's because it's so high and because it's in Chile, it's exceptionally dry there. So you can see well, very well in the submillimeter band. Submillimeter band is absorbed by water vapor in the atmosphere. And that's why, and it's the same frequencies at some level that are in your microwave. So it's the A and B thing. They're related, those things. We're going to do a bunch of science that I'm going to go through in detail. So where is it? It's in northern Chile, here Santiago. So when we go there, you fly typically to Santiago, then fly north to Antofagasta, or the other one I have trouble finding, Calama. Calama. And then you drive. And you drive up to San Pedro de Atacama. It's a nice tourist spot there. The first time I was there was in '99, and it was a very relatively quiet tourist spot, but it was very notable, and it had scads of people your age there from Europe. They're all European. And but it's a very interesting place. It's got a Spanish heritage, of course, and also the Inca heritage. And so there's Inca ruins and stuff up there. It's pretty fun. And let me see. So it's This area is high and dry. It's on the west coast of South America, as you know, and as a consequence, it has excellent seeing as well. There's mountains sticking up right by the ocean, and a lot of you have heard me say this before. When you have the air flowing across a uniform temperature thing like the ocean, it gets nice and calm and uniform and laminar, we call it. It goes across the mountains, and the seeing is very good. So you have excellent seeing. So there's a lot of optical telescopes as well in the area. We are specialized, and the Atacama region itself, is San Pedro region of it, is specializing in submillimeter work. It's adjacent to the Atacama submillimeter array, and it's absolutely gorgeous. Now, I stole this picture off the web because I couldn't find my pictures and they're not as nice, but it's absolutely gorgeous drive getting there. And you can see these volcanoes in the distance as you're flying along the coast of Chile. And that is Volcan Lincacabur, which you see all the time from Atacama area. It's 5,900 meters, I think, high. It's really quite tall, and it's not normally covered with snow. But the interesting thing about that is that I've been going there for observing for apex. Oh, this was supposed to be something that flew in, and you're going to be thinking, you guys, those guys that know me know I'm really good at this sort of stuff. But it's a joke. But there, we've been going. My research group has been going there since about 2013, and once a year or so. And we put our instrument on the Apex telescope down there. It's a telescope already there. It's one of the prototypes for the Atacama array, and it's a really, really pleasant place to be. And in about 2020 or so, after having gone there maybe 8 times and staying for, at least 2 weeks, I got there and I saw the picture. I saw the volcano really nice from right where my room was. And this is a picture I take, you see this all the time. And I sent it to my wife, and she says, why is there a volcano where you are? Why are you near a volcano? I said, I've been telling you, for N years that it's near a volcano. It's really cool and you should visit. But it's really nice there in that regards. And I'm giving you a little tour of how to get up the mountain because that's fun. And on the, oh God, everything's going faster. There's supposed to be something underneath, I think. On the way up, you get the wild donkeys that used to be domestic, and they're running around. So they get in the way. And then these vicuña, which are like llamas, but they're not the same. And they're absolutely gorgeous. Really cute, as you can tell. And you drive up the road, and I couldn't find the picture that I got once where we were behind the very last telescope being moved to the interferometer site. So this is the ALMA array. And this looks like a little compact configuration or a younger version of the photo. But this is what it looks like when you get to the apex site. The apex site and the ALMA site are about 5,000 meters. So they're 6,600 meters lower than where we're going. And it's absolutely gorgeous up there. And you can see these are all 12-meter telescopes. There's 50 of them when the whole banana's going. And so they take them up and down the road for refurbishing from time to time. So that's one of the fun things that happen as part of the venture. So here's a picture of a heroic team. We went during 2021. So the pandemic wasn't quite over, and they could only let 2 people go. And so they sent us us old guys from the team went down there. This is Thomas Nicola. He's a PhD that's worked with me for 25 years, and he does everything. He's brilliant with the instruments and stuff. So there's us after we were observing, and the background is Cerro Chatanuntoro, the big mountain that we're on. So is that the last picture I had? I thought I had another. So we're going to go on top of that mountain. And why are we going there? Well, we're going there to pursue science. And a lot of the science actually revolves around galaxy formation and star formation, right? And the structure of the universe. And so many of you have seen this plot before. It shows the evolution of the universe in some very compressed scale. where the first incident there was the Big Bang, right? Everybody knew that one. And thought to be inflated by the inflationary epoch, and grows many orders of magnitude. I think it's 10 to the 27 orders of magnitude in 10 to the minus 34 seconds. From the size of a cherry pit to the size of the current horizon is what that distance ratio is. It's really astonishing, but it's a thing that people invoke to make the universe look as homogeneous and isotropic as it does, because everything got stretched. So all the quantum fluctuations of the earliest times were stretched out. Things got uniform. After that, 380,000 years passes, and the universe has cooled until it's about 3,500 kelvins or so. And by that time, before that, of course, everything was fully ionized, and it's just hydrogen and helium. And at that time, the temperature drops enough that the electrons can combine again with a hydrogen. Before that time, the electrons were in there and the photons were in there, and the photons are scattering off the electrons because there's electric fields and electromagnetic waves, and they're scattering and they're coupling very well, so they have the same temperature. And because they're scattering and have so well, the electrons cannot collapse under gravity very easily, because photons are yanking them around all the time. So no gravitational condensations are forming, except dark matter. Dark matter doesn't interact with photons, right? So it can start collapsing. In fact, this is a key element of how we understand galaxies form, is that dark matter started collapsing and forming over densities, over quantum fluctuations that are found in the universe in the earliest times, and start building up a structure, which is key for the buildup of galaxies today. So once the electrons combine with the photons, the cosmic microwave background radiation is freed. And then we get to this totally misnamed dark ages. I hate that name, but everybody calls it that. And then when I complain, people say it's because there's no new sources of light. There's still the cosmic microwave background radiation. The universe is brilliant. It's not dark. But it expands. The photons get stretched by the expansion. The temperature of the background goes down. It gets to a point about 400 million years where matter is released from the photons. So matter can start streaming towards the overdensities that are being formed by the dark matter. And so you start getting star formation along this. You've seen the pictures of the dark matter. It looks like bubbles, right? The soap bubbly structure of the universe that we know is correct. And the reason I say that with some surprise in my eyes is because certainly when I was your age, and back in maybe about the year 95, or no, it was a little earlier, it's 85. So back when I was about your age, people were really astonished when they started. Martha Haynes was one of them. You guys know Martha. That to discover that the distribution of galaxies made frothy bubbles. And after a while, people started doing, they got some more information, and they got the implications of that new information was that there had to be condensations early in the universe. And then when you make more and more sophisticated models, you realize this is important. That froth, that bubble structure where the galaxies seem to form on shells and strings and lines and this and that is important. So first stars, galaxies formed about 400 million years after the Big Bang. And then you keep the expansion, and I push a button because we have ways of addressing these things. The first epoch is the reionization process, because when the electrons combine with a hydrogen, it was a neutral medium now. And now today, the intergalactic medium is fully ionized. And so the galaxies and quasars, mostly galaxies, start reionizing the universe. And that went from about redshift 20 to, which is something like a few hundred million years after Big Bang, to about redshift, 5-ish or something like that, which is more like 2 billion years after the Big Bang. So we have an instrument to do that. That's one of our surveys. We have instrumentation to trace the dusty star formation history of the universe. I'll show you details of that. And that is happening from about the time the first metals were being created, maybe 100 million years after the Big Bang, to more or less the current day. And then we have tracing out the growth of large-scale structure in the universe, which we do with the surveys, both the first surveys and also with the Sennyev-Zoldovich effect, which will heretofore be called the SZ effect, because my Russian is about as good as my German. Ganz schlecht. We also will address the very early times of the universe, the times of inflation. That epoch, 10 to the minus 34 seconds or something like that. We can address that by looking by the imprint of inflation on the magnetic field modes of the cosmic microwave background. Kind of exotic stuff, and I'm not an expert at it, but we can tell by the shape of the magnetic field whether inflation happened, or at least get a handle on that. And we look at galactic science too. So I have instrumentation to look at the Milky Way galaxy and nearby galaxies in the sub-millimeter bands through photometry and through magnetic field tracing, which is polarimetry, and through spectral lines. And finally, we'll do time domain science, which means, the one thing I'm going to talk about is the thing that's less obvious to everybody, and that's protostars. When they are creating matter, they flare because the matter gives up its potential, becomes kinetic energy, and there's a flare when it accelerates into the star. So all these projects are large field mapping projects. That's what our telescope specializes in. So you need a large field of view, very sensitive instrumentation, because a lot of these are extremely difficult. The surveys I'm going to describe, 2 of them last 4,000 hours. So it's a lot of time. And you need a very good telescope to minimize the time. High surface accuracy, low emissivity, and extraordinary submillimeter sight. So this is the telescope and a couple details about it. I'll show you the optics in more detail on the next slide, but there's a primary mirror here that immediately reflects to a secondary that's over here and then into a bay there. And so because it's doing that and there's no secondary in front of the mirror, we get rid of one cause of issues, the secondary. The secondary has all these things that it does to the point spread function, makes the stars that you see, the diffraction of the rings and stuff like that. And those secondary support also takes ground radiation and deflects it into the detector. So it makes it a little kind of some systematics that are hard to get rid of. And the third thing is that they also have emissivity. And so that means power comes in. And the more power that we come in that we don't want, the worse our sensitivity. So our sensitivity is limited by the statistical arrival rate of photons from the background. And the background is hot things in the beam. So in a really bad wavelength, which I've traditionally worked in the short submillimeter, which it's always the sky's always only 30% or 40% transmissive. We have a lot of background. It's because the stuff that's not transmissive is emissive by Kirchhoff's laws. And so you get all those photons coming in, and their statistical random arrival rates make noise. So we want to get it really cold, and we want to have the very wide field of view so we can do the surveys in a reasonable time. Very high surface, actually, very smooth, so we don't lose power from scattering. No blockage. Already said that. Has to scan fast because the sky conditions are varying at time scales of a second. So we want to have beams that go across the sky time scales of at least fast a second. So we got to be scanning fast. Got the really high sight that gets rid of the water vapor or gets rid of most of it, and the elevation range helps us with systematics, and we have some really cool instrumentation as well that I'll mention a bit. There's this actual artist rendition, isn't it? So this is the ALMA array, and that's where it is, and we're up on top of that mountain. So we look down on ALMA, the billion-dollar project. So we have a great telescope. We put it at a great site. So the first thought was, why not put it at the same site as ALMA, which is 5,000 meters, and then a few extra thoughts in calculations and measurements. So Riccardo Giovanelli and others, I was on one of the trips or 2 of them with him. We measured the water vapor above the Chattanooga plane. Chattanooga plane is at 5,000 meters. It goes a long way, and it's a plane. It's called the high plane. And we found out that the amount of water that you could precipitate out, if you took all the water, for example, in above Fuerte specifically, and precipitated it out, it'd probably be 10 centimeters or something of a minor lake. And if you go to Hawaii, where I've done a lot of observing, it's more like 1 or 2 millimeters. And here it's more like less than a millimeter. And up in Chattanooga, it's about 0.4 millimeters. So it's a big difference. And so that makes a big difference in our sensitivity. And that's reflected in this plot here. I basically calculated how fast we could map things at as a function of frequency for the two sites, and the ratio of up high versus down here, same telescope, same everything else, is a factor of 4 faster. So instead of taking 4 years, it takes 1 year. And that's in the short submillimeter bands. But even in the millimeter wave, it's where the atmosphere doesn't get hurt as much by water, it's still a factor of 1.5-ish. So it's a win, especially at the high frequencies, a very substantial win. There's the optics. And funny configuration. Let me go through that far. Light comes in from the top, hits the 6 meters, a little bit more than 6 meters, goes back this way, and then forms an image plane here that you can see is enormous. That image plane is, 3 meters in size or something. We only take about 1.2, little over about 1.5 meters, a chunk out of it right now. When you get further off axis, the goodness gets worse. So these are frequencies, and this is the Strel ratio, a measure of how good it is. If this is diffraction limited at 870 gigahertz, which is 350 microns, I go to lower frequencies, the wavelength gets longer, so it can be rougher and still be diffraction limited, as you might, intuitively think. So the field of view is enormous, measured in, meters. And so therefore it's very hard to pull a vacuum on something a meter in size. So we break it up into smaller tubes, and each tube has a window of about 40 centimeters, which is still kind of a big window, but it's manageable for thermal, because we move our detectors down to 100 millikelvins, and also for vacuum. So we make these little modules there, and they all have transmissive optics. They're made out of silicon. That's a technology challenge as it right there. And then we put those modules together, and we make a 7 tube configuration. And these are the numbers of pixels you would get if you filled the focal plane in a reasonable way. You get about 100,000 pixels or more, depending on exactly what wavelength you want to do. So this is what the instrument looks like. It's got this 6 tubes around one tube, and you can fill those tubes in with various types of receivers. We call them receivers more than, because this wavelength, you tend to call them receivers instead of instruments. And these are the frequencies of the of the polarimetry cameras. And this is the spectrometer channel that my group is specifically working on, that will do the light intensity mapping that I'll talk about. There's also a heterodyne receiver, which is a receiver that can get very high resolving power and really resolve lines. And so that's being worked on by the group at Cologne. So that thing happened. Okay. It just tapped on me. Beautiful image. We've all seen this. It's astounding, right? And come on, it's beyond belief, right? And this is like first light. So happy times, really great stuff. You wonder, why anybody else bothers to do anything. There's reasons, and I'm going to try to convince you there's a reason. And so that came out a couple of years ago, right? So JWST works in a band between about 3 microns and 26 microns. The stuff we're doing is from 350 microns wavelength space to about 2 millimeters or so, a lot longer. And that's important because we're seeing different things. And what this plot is, wavelength and power. And this is looking all over the sky and getting a handle on how much power is coming out at what wavelength. So if you didn't know anything else, you would probably say, okay, stars are, 5,000 degrees, 6,000 degrees. They peak at 6,000 or 5,000 angstroms wavelength, Wien displacement law. And then, so I would expect that I'd see a lot of power at those wavelengths. And so this is 1 micron. So that's 10,000 angstroms. There's a lot of power. So these are the stars. That's the stars. And then, so people have mapped it out and they get the glow from the universe. And then what happened is in 1990, I think it was, the COBE satellite discovered that there's a cosmic infrared background. The COBE was the fantastic first CMB experiment that showed the perfect black body spectrum, Nobel Prize. And they also measured an infrared background, much to the surprise of everybody. But when you look at A and B, you go, oh my gosh, the infrared is as big as the optical, which is a big surprise. And there's a raison d'etre, there's my French badly spoken, for infrared astronomy. That's the game. Half the light ever emitted in the universe comes out in the infrared. So what gives it, how does this work? Basically what happens is that stars are formed in dusty clouds. The size scale of a dust grain in the interstellar medium is about 0.1 microns. The size of a visible photon, the wavelength of a visible photon is half a micron or so. So that dust grain and the photon interact very strongly together. And so the dust grain can absorb that photon's energy. And if it does that, it heats up. And for the Milky Way, the average grain heats to 20 Kelvin or so, and then it glows in the far infrared. For starbursty galaxies where there's lots of action, they heat up to 50 Kelvin. That's basically what this is. This is re-radiated starlight that's coming out in the infrared. And it shows you that if I just studied optical stuff, which is essentially what JWST does, I'm going to miss a lot of the star formation in the universe. And that made me very sad. Okay, so I think I said all that. So here's, why do I have two infrareds? Nobody knows. So here's an example of M31. M31 is our neighbor, right? 600 kiloparsecs away in the visible and in the infrared. And if you superpose these two things, you'll see the glow lines up with the dark because this is dust lanes and they glow in the infrared. So that shows you the different view you see just of the Andromeda galaxy. And here's a fun all sky projection of the Milky Way. That is really a cool picture. But you can find them everywhere just by Googling. It's the Google. So the feast field of view, we have 7 tubes, each of which is 1.3 degrees in diameter. And the field of view is of JWST. So if they were even working at the same wavelength, it would take JWST 11,000 times longer to map the same region in the sky. So we're going to spend about 4,000 hours doing our surveys. And for JWST to do the same thing, it would take maybe 11,000 times that. 1 hour translates into 4 years. So it's a tough thing to do. But the bottom line is we're doing different things, right? They're doing high spatial resolution. They're looking in the near infrared and mid infrared, and we're doing submillimeter band stuff. So the science cases. Yeah, I got plenty of time, 25 minutes, right? Okay. The science cases are galaxy evolution is the first one I want to talk about. And so these are actual data from the Herschel satellite, which was running about 20 years ago. And it did a really nice, deep image of the universe in submillimeter bands, 250 microns, 350 microns, 500 microns. These are different colors, different wavelengths, different colors. So you can get the spectral energy distribution, effectively the color of the black body that you're tracing out. So you know how hot the dust is or how far away it is if it's redshifted, right? And so if you look at this thing here, you see a motley crew came to mind. I don't know why. A motley distribution of bumps. And they're so close together that you can't tell if this is one bump, two bumps, or what. And we call this the confusion limit. And so this was taken with a 3.5-meter telescope in space, spectacular mission. And ours is 6-meter. You wouldn't think the different confusion limit is driven by the number of sources you have per beam. The beam is your spatial resolution on the sky. And so this guy had a beam of about 30, more like 50 arc seconds or so. You guys have a good feeling for that. I think most of you are in astronomy. I recognize so many faces. We're going to have about a third that number. And so that means you're going to pull the point sources out of the model crew. And once you can do that, you can start getting individual sources and trying to figure out what redshift the sources are by looking at how the dust has shifted, the wavelengths of the dust has shifted. So that's the first thing that we're going to win with. And we're going to start, I can skip that one before that. I realize this is a graphical distribution of how important the infrared is. Oh, this is important. So this is redshift. Redshift 0 is today. And then redshift 8 is getting kind of into the epoch of reionization. And it's been well mapped, the total amount of star formation in the UV out to maybe about redshift 2.5. And because of the Herschel surveys out to the same sort of redshift, and you can see there's a difference of more than a factor of 2. So it becomes, this is 0.5 square root of 10, right? So it's 3. There's 3 times more star formation occurring that's in dusty cocoons than the stuff you can see with Hubble. It's kind of cool. It's hidden stuff. So that's part of the game. And when we go and look with our cameras, this is the illustration of what Herschel saw. And when we get the same place, same demonstration with a smaller beam that we have, can break apart all the sources. So you can see the point there, I think. We're going to do a bunch of wavelengths. And if you do a bunch of wavelengths, you trace out the spectral energy distribution. It looks sort of like a black body. It's a modified black body. And so we know typical dust temperatures are going to be 30 degrees for these things. And so we look for the peak of the 30-degree black body. How much has it shifted? Tells me how far away the thing is by the redshift law, right? And so therefore I can get the luminosity. I know the power from measuring the flux, and I know the redshift by measuring this SCD and how it shifts. And the combo gives me the luminosity of the source. So we measure the evolution of the universe in terms of luminosity too, which is incredibly important to discern whether galaxies are forming by major mergers or raining down small things. The bottoms up, where you rain together little things, and the top down, where you take big guys and slam them together and make even bigger guys. So the line intensity mapping is the thing that my group is focusing mostly on. And basically we want to trace the evolution of stars and galaxy formation and the evolution of structure in the universe over cosmic time the best we can. And you need to do this, you need large-scale tracers of the source material. Stars are formed from hydrogen. Star formation, which I get that out of spectral lines. My favorite is the single ionized carbon line, which was my thesis topic from about 4 years ago. And the structure, ideally from the size scale of individual galaxies, 30 kiloparsecs or so, to that of the cosmic web overdensities. Those overdensity scales are tens of megaparsecs. And so you can see these are the demos that people do, the models, where you have dark matter building up structure that I was describing, the soap bubbly structure coming. So that's the origin, or not the origin, redshift 27, which is almost at the origin. That's like 10 million years after Big Bang. And then you go through redshift 5, and you're building structure up slowly until modern day you get what we see. So you need 3-dimensional maps. You need X and Y, because I'm looking for this structure, and I need Z, so I know how far away things are. And Z is redshift. Z happens to be as well. And so we can build up the structure of the universe that way. So we want to measure structures on the scale of megaparsec, which is roughly the distance between us and the Andromeda, and 30 megaparsecs. And so that's up to from arc minute scales to 2 or 3 degree scales. And we'll ideally you'd see stuff like this. We're not gonna, but ideally you would, because this is the underlying dark matter, the stuff that star formation lays on top of that makes it a little messier. So we need the big scales. The good news is that you might think, why don't we just go and measure all the big luminous galaxies with a telescope and map it out? Well, it takes forever. If you have a big telescope with a little beam, you can go very deep because there's no confusion, and you can really study an individual galaxy and learn a lot. But you can't get large scale structures because it takes forever. So the good news is, if we take a bigger beam, which takes in 50 galaxies or something like that, I'm exaggerating, 10, 20, the power from that is detectable with a small telescope. And it turns out these little galaxies that make up the 10 or 20 are the dominant sources of star formation in the early universe. So I'm basically summing up the emission from the little guys with big beams and mapping big areas because I have big beams, and so I have a huge focal plane and I can go fast. So it's much more efficient to do it with our modest sized telescope as we are doing it. So we're going to be doing it with the C+ line, which traces the intensity of star formation. Other people are doing it with other telescopes in the 21 centimeter line, tracing hydrogen. Other people are doing it in CO lines with other telescopes. We'll get some of that too. That traces molecular hydrogen. It's got the carbon and oxygen in there too. So that's something to do with how the metals form. So there's some science there too. H alpha, that's the signal that the red stuff around nebula, right? That's the signal of star formation as well. And so we'll mix it in with the other people's result and hopefully detect the signals. The signals are weak. Ideally they would look like this. We'd see spots of C+ emission at different redshifts, and you can trace the structure as it changes over redshift and see if the bubbles are getting bigger or smaller, and are, and all sorts of stuff to constrain the evolution of the structure of the universe. And also the intensity of the line constrains the evolution of the intensity of galaxy formation. So it's a lot of useful information coming at once. In reality, we probably we'll see something more like this and faint. It's a tough experiment. It takes 4,000 hours. And we'll put it in the Fourier domain, because we're interested in the relationship between point X and point Y in the sky as far as the angular distance, right? I'm trying to measure bubbles, right? So if I have a ring on my image plane and I do the Fourier domain, I'll get a little spike in power where everybody's the same distance apart. And so that's sort of the idea. So we put it in the Fourier domain, and the red lines are us. The other lines of the competition, the other dotted lines of the competition. So in principle, we should win. But the other things on these plots are the predictions. So we're going to very likely have nice detections at those redshifts, but when we get to higher redshift, it's going to be a tough go. It's not easy, but we might get surprised. So that's the experiment I'm most interested in. There's also cosmology. This one's harder to explain, but there was a false detection. Do I have time? Probably. Yeah. Okay. Most of the end ones are pictures. So there was a false detection of cosmic B modes, which is a type of polarization imprint on the cosmic microwave background. You can get that imprint from both inflation. It's predicted to happen in certain types of inflation. And that would be fantastic if it's true. And you can get it from properties of dust in the Milky Way galaxy. So there's the ouch. And so there was a reported detection of that thing with all sorts of celebration before they realized it was wrong. And what happened was they weren't taking care of the dust well enough, and they didn't have enough data to do that. And so what CCAT brings to the table is that we're doing high frequency measurements of the dust. And it turns out the high frequency measurements of the dust emissivity and polarization enable you to make corrections for that galactic foreground B mode polarization properly, and removes a bias from the measurement. So the predicted and the measurement is put in units of R, which is the cosmic tensor to scalar ratio. And so that basically the number that is expected is a very tiny number. And if you don't use our high frequency thing, and we are expected to have a bias in our final number that's of the same order as the answer. So putting in our measurements gets rid of the bias at least, but it's still going to be a tough go. So this is something that's one of the holy grails of people that do CMB studies that'll probably only emerge partly from our contributions and partly from other big observatories. There's the SC science, the Sunyaev-Zeldovich effect. So if you have clusters by their nature of galaxies will have hot gas in it because there's an equal distribution of partition of energy. You probably heard that phrase. And so the electrons are moving around fast and they're emitting X-rays. And they also, when the cosmic microwave background comes through them, they inverse Compton scattering. And so some of them pick up energy and some of them lose energy. And so you have hot spots and cold spots on the sky. And those are the effect of the SC effect. So there's a thermal, that's the easy one that I just described. There's a kinetic, which is basically the movement of the cluster with respect to the expansion of the universe, the peculiar velocity. So that'll actually shift the spectrum by the Doppler shift. So you can tell whether it's moving away from towards you. That's kind of cool. We are moving with respect to the cosmic microwave background by about 300 kilometers per second, for example. And then there's a relativistic, which measures the temperature of the electrons in the nebula. But you get some really cool stuff on that. Basically, you might guess that when you're mapping the accelerations relative to the rest frame of the universe is the cosmic microwave background, right? That's the rest frame. Moving with respect to that, I can tell if there's a gravitational field over there pulling me and things like that. So you map out the structures and the gravitational fields, and you start getting, if you really go deep enough, you start getting answers that will eliminate the funny theories of gravity that some people like and stuff like that. So it's good stuff. And things about the early universe, how much mass neutrinos have and things like that. And finally, not finally, but nearly on the science is a polarization science. So these are just some pretty maps of various things. So this is a nice map of the galactic center. And you can see how the ring around the galactic center has warped the magnetic field lines. And then there's infall along these magnetic field lines towards the black hole right there. And it's thought that the field lines control the collapse of molecular gas, because as you know, charged particles don't like to cross field lines, they like to spiral around them. And even with neutral gas, there's some charged particles. Those guys are spinning around and they're colliding with the neutrals, and so the neutrals do the same thing. So they sort of funnel things into certain properties of star formation, which are disk formations and things like that. So that's the stuff that people are going to be studying that are doing the galactic polarimetry. And there's people studying transient phenomena, time domain phenomena. And one of the things that I hadn't realized how cool it was that when people look at and they monitor protostars over periods of time, these are Julian days, I think. Yeah, so periods of time of hundreds of days or thousands of days, they see flares. And that basically means there's an accretion disk around the star and it's dumping some energy onto the star from time to time and building up the mass of the star. So it's real-time observations of the growth of stars. And finally, galactic ecosystems with CHI. So CHI is a heterodyne receiver that's designed to probe carbon-1 lines and CO lines. And it basically, they have high velocity resolution. So they look through the galaxy, and the galaxy has a rotation curve. These lines trace the density and the temperature of the gas. So they get a measure of the temperature and the density of the gas along that line of sight. They line it up with things that are known to be star formation regions and can map out the star formation in the Milky Way galaxy. Oh, double feature. Okay, so a bunch of people at Cornell involved in this. Martha Haynes is a CCAP board chair. Jim Blair is project manager. Steve Parsley, a project engineer. He was a master's student of mine back in 2005, wintered over at the South Pole. Amazing engineer. And here's the adequate director. And then Mike Niemek is an amazing a physics professor making instrumentation. And Nick Battaglia, a project scientist. Abby Kreitz making the next generation line intensity mapper, spectrometer on chip. Anna Ho is a new faculty member. She's the specialist in a high redshift time domain phenomena. Somebody throw out the names of some of them. There are things associated with AGN and stuff like that, and exploding stars. I'm messing up the detailed names, but they're basically high energy phenomena that are short time scale. Dongwoo Chung, line intensity mapping expert. This Drummond Fielding's brand new, and he's an expert on galactic formation and evolution. And Thomas Nicola has worked with me forever, and he's expert on everything as far as I can tell. So this is the prime can instrument. This is a report. So let's go. I'll be done, I think. This is the picture of the instrument, and this is the predecessor. It's the ModCam. So this guy is just holding one tube. This is how big one instrument tube is. So the team is putting it inside the cryostat. They'll belt it in to the thermal conduction units, and there's a cryo cooler that'll get them down to dilution refrigerator, they call it. That gets down to about 50 or 60 millikelvins, very cold. And that's necessary to make the detectors work properly. So this is not any sort of magic, the temperatures. It sounds magic and if you haven't heard it before, but people have been doing this for a while. The people at Cornell were in the low temperature physics lab, which it used to be called, were getting in microkelvins by using funny devices. So there's expertise here. That unit is our big one that won't be on first light on the telescope. But as I said, it has 7 units, one of which will be the thing we're building. And we'll hopefully have this one on the telescope as well at first. This one will be on at first light because that's really good for the SC and the dusty star from galaxy stuff. And then we have money to build this one, and this one, and this one. And we're trying to figure out how to get money to do more. We have partners joining as often as we can. So next slide. God, am I clever? I'm populating the thing. Okay, so here's some fun stuff with the detectors. Some of the arrays exist. They're called kinetic inductance detectors. And the idea here is that you have a superconducting coil. So this is made out of superconductors. There's an inductor and a capacitor. So they have a natural resonant frequency, right? And then you tap it into a feed line and tap it capacitively into ground. I got it backwards. A capacitively into the feed line and directly into ground. And so if I feed a variety of frequencies in there, the one that matches the resonance gets sucked to ground. And when it gets sucked to ground, you see an absorption feature. So it tells me, I see this detector. The depth of the absorption feature tells me how strong the resonance is. And the position of the resonance tells me what the units of inductance and capacitance are. So the key, just change the units of inductance by putting photons in there. So the photons come in and they break the Cooper pairs that are the superconductors. And so they change the inductance and they change the phase of the signal as well. So they're a really nice, simple detector in principle. That you can use to detect microwave radiation. In fact, all kinds of radiation. They're even used in the near infrared. And you're reading them out with the same sort of electronics that operates our phones and stuff. It's the same frequency. So that stuff is really well developed, the gigahertz stuff, right? So that's a really nice way to read them out. And that's a big, the up and coming technology. It's much simpler than the stuff that we've used, that my group has used in the past, which is called transition edge detectors. So some of the parts. So this is the big doer. It's giant. It's more than 2 meters here. Yeah, so it's big. You can have a party in there. And then there's a layout. And here's somebody working on the rings for it. This is being delivered by Redline. So this contract is overdue by about a year and a half, but we hope that they'll get it to us by the end of this year. But I would have said the same thing last year. So it won't be on first light in the telescope as a consequence, but the other stuff is taking time too. So it's not a cripple. So we do have this one ready. I showed you the grad students putting the thing together. And this is called ModCam. The woman that led this charge, Eve Babagiakis, I can't pronounce her name. I've known her for 10 years. It's a Greek name. And she's a now professor at Rutgers. And she's still working with us, doing great stuff. She's absolutely great engineer type physicist. So those are the details of the instrument. You can ask me if you like. And there's the parts of our instrument, the spectrometer are showing up now. There's the outer tubes for it, and then the detector array being tested at, getting ready to be tested at the 50 millikelvin level. And Rodrigo Freund, some of you probably know, he's from my floor in the building. And it's run by a Fabry Pro. So I won't go into details of Fabry Pros, but if you want, I could talk forever on those. But that's what we're using. And you basically spectrally scan across and get the frequencies from 210 to 420 gigahertz. And they make an image at every frequency on the array. You put them together, you have a spectrum. Quite simple. And oh, that was my demo. Pretty impressive. I'm sure you saw it. Oh, is that a double shot too? Sorry about that. And here's the beast, Feast, the beast. So this is what it looked like in September 30th. It was all built except the mirrors aren't in, as you can tell. So it was all built in Germany in a place called Wessel on the Rhine. And then it's now getting torn apart. But before I tell you about that, yeah, why aren't the mirrors on there? It was the mirrors are behind, and I think I might as well. No, maybe I don't want to record it, but they're behind. No, there was the company that was making the mirrors did something not intelligent. They made all the mirrors, and the mirrors look like they're the same on the left side and the right side, and they assumed they were the same, and they're not. They're slightly different. The dimensions, they're not really rectangles. They're, it's like trapezoids by 2 millimeters. You can't see it very easily because each piece is 70 centimeters across. But when you try to put it together, it doesn't fit. So that was discovered, but it'll be okay. They'll just shut the mirrors down later. It'll be fine. And so here's what the mirrors look like. You can see all the fancy metrology. You have to keep these mirrors aligned to each other within a few microns, about 3 microns. The overall surface has to be 10 micron accuracy, which is pretty good. And this is the shutter. That was a newly installed thing in September, so that we can keep the weather out. And they purposely put a thing here. So you walk here, don't walk there, because you're on top of the telescope in principle. The telescope is about the size of the Space Sciences building, the whole thing, right? It's pretty big, even though the mirror itself isn't gigantic. And here they are taking it apart, getting ready for shipment. And there's been a lot of stuff going on at the site. This is where the fuel is going to be right now. Unfortunately, we're running diesel. We hope to get a donor to buy stuff to, solar panels. And there's the diesel tank, 80,000 liters. And there's the summit area. It's all fenced in. It's more developed than it looks because, for example, that thing is actually dirt piled on top of this thing to protect it until the telescope arrives. This is the pedestal for the telescope. So it has an enormous amount of concrete linking it into the bedrock of the summit. Last slide. This is the schedule. They're preparing to ship it to Chile now. And they told us last that I heard was 3 days ago that, yeah, it should be there. It should be shipping by January 1. It's always scary when it's shipping around the holidays, right? Then they'll assemble at the site starting in March 25 in just 4 months, right? And then be done about within a year. and turn over the keys to us. So the people that made the telescope will set all the panels to about 30 microns accuracy, so not as smooth as we need it. And they do that by photogrammetry, which is photography, measuring the distances. And so that's pretty cool. You can do it that accurate, right? And then we'll take over with holography, which uses the wave fronts and millimeter waves, and take it down to the appropriate level. And then the scientists are taking it. Well, the scientists will be working with our engineers in the earlier months of 2026. This date, we're supposed to be taking it over with our instruments and getting first light no later than this date, hopefully sooner, between those 2 dates somewhere. So that's our status, and it's a really fun project, and thank you for your time.
Thank you so much. If we have any questions, feel free to raise your hand. And if anyone on Zoom has questions, feel free to type them in the chat. Any questions? Ben, and you're gonna have to repeat the questions so everyone can.
No, yeah, I was really astonished by them, and then I remembered T-Tauri stars. Yeah, and so T-Tauri stars do stuff in the optical. Yeah, yeah, I thought, wait a minute, but this is a better thing because, well, better. I'm biased, right? Because I've done far infrared and all my life, but it tends to measure better the energetics. The luminosity is more closely linked. Mostly probably because the light all gets out, right? Because they're in dusty areas. Yeah. Yeah. Oh no, you can get very precise. Yeah, I mean, so what people do is there's a lot of good examples, but Orion's our first example always, right? I mean, a long time ago, when they were first doing far infrared work, which was in the 70s, they from the airborne observatories, they measured photometrically the light spectral energy distribution, the power as a function of frequency, for the BNKL object named after the two guys on the airplane that discovered it, which is the embedded hotspot of behind the Orion Nebula. So the nebula has a trapezium, you guys all seen that, and the H2 region, and behind it to the upper, my left, and so to the, west, northwest. Yeah. And I'm trying to think, was I driving or not? Yeah. You guys have that problem? Whether you're driving or looking at the stars, east and west or backwards. Okay, but it's to the northwest, about an arc minute from the trapezium. You don't see anything in the optical, but if you look in the infrared, there's an incredible bright spot, and people map very accurately the distribution of the energy, and it matches a black body with a modification to it, and the emissivity law of the dust usually is 1/lambda, which means that dust is less emissive at longer wavelengths, and that's because you need the dipole moment of the dust has to be about the same size as the photon, right? So if I have a big photon, it doesn't radiate very well from a little dust grain, and it doesn't get absorbed very well for a little dust grain. So they have to put the modification in there and make a match, but then you get nice confident numbers. And you look around the galaxy, and one of the things that people like to do that are into this is see how the properties of the dust grain change as you go around different environments, and they find really cool stuff. They get the distribution size of the dust. There's big guys and little guys and tiny guys. Yeah, so it's pretty fun.
But some final announcements. Thank you so much, everyone, for coming. As always, we are open 8 to midnight. Clouds look kind of abysmal today, but we still have our historical telescope. So we are going to head over there right now, and let's give one final round of applause.